Hello everyone. In this deep dive video, we are going to take a closer look at the different workflows that we can use within the InStep Studio application as it relates to reverse engineering different types of files. The first thing we're going to do is we're going to work with a file that's more geometric. Specifically, in this case, it's a PCB file. We're going to go ahead and import it. And depending on what the file filters are set to, we may have to change that. In this case, I'm just going to switch to the common format, and I'll find my pcb.obj file here. After a few seconds, the file loads, and we can take a closer look at this by turning on the edges with Alt and E. And we can see there's a number of components populated here. These are generally just placeholders based on the export from the design package that this was created in. Some users might be tempted to directly go to export and just save this as a step file, and I'm going to show you what that does. So we just call this pcb.stp, click save, and I'll go ahead and save. And after a few seconds, we'll see an output in the message field here that just says 5.4 megabytes in 4.2 seconds. So if we go ahead and import this, and I'm going to use a Libre Design for this case, we can simply import it as a step file. It'll ask us about some healing options. I'm just going to leave these all at their defaults. And in this case, the import can take several minutes, and the output is shown here. Now it does show that the file was imported without errors, and it was internally split into a number of subcomponents, so this is all fine. And we can see that we have individual components. They weren't given any color information, so they all come in as black. But in general, this would be an acceptable way of converting the data. So in this case, this wasn't quite what we had in mind, so we are going to go ahead and close this and proceed through the actual process that we want to show here. So the first thing to point out is that if we just go ahead and export this as one set of data, the application won't be able to do much in terms of determining what different components are and so on. So the first process will often be that we go to bodies and then split the data. We can leave the defaults on and go ahead and click preview to get an idea of how the application thinks the different components are laid out. And in this case, we can see by the colors that it recognizes different items and splits those. So we click apply to make that change permanent. Now, in another tutorial, we showed how we'd work with the PCB directly, and we could go ahead and select that and then delete all other bodies. However, here we want to keep all the components in case we wanted to use those for something else. So the first step in the reverse engineering would be to convert all these more complicated items into feature-based definition. For that, we have a separate tab, the Features tab. We click here, we leave the defaults on, those are fine for now. Click Preview, and the application will go through and it'll try to determine the different components for each item. So here we can see that it's found cylinders, it's found what we call polys, which are just a set of surfaces that are flat with some kind of perimeter inside or outside. And then we have a whole bunch of the quads. And the quads are appropriate for all these smaller components which are just represented by a box. We can also use the random color option to see how these items are separated internally. And we can see that these have separate ends to them. So that's what we're looking for. If we're happy with that, we click the apply and make that change permanent. So after just a few seconds, we're now left with the bodies, and individually these were converted to a more reasonable representation. One item to note on the Features tab is that for whatever reason we're not happy with this, we have the option of going back to a triangular representation. So clicking this would essentially just undo the feature conversion that we've done so far. It should also be noted that all the other tabs are no longer available because we now have a feature-based definition, and all these tools are laid out to use feature-based definition. So in this case, again, we go to export, step, and we're just going to go ahead and overwrite the previous file. Note that the original size was about 5.4 megabytes. And once we're done, we're left with a file that's only 0.3 megabytes. It's also done a lot quicker due to the different size. Again, we're going to go into our Libre, and we're going to import that file. We'll leave all the options on. And in this case, the import actually only takes about 30 seconds. And again, this will vary based on the number of features and details so on. But we also get the feedback that the file imported without errors. It internally split it into a number of assembly components, and overall this looks fine. So if we browse around, we can see that all the features were correctly recognized. And the most interesting one here is obviously the PCB itself. If we take a closer look at this, we can see that the holes are actually defined by arcs rather than just splines or a number of edges. So this would be a perfectly acceptable output for use in whatever mechanical design this is intended for. It should also be pointed out that this is just an example, so Libre is not the only application that can use this, since the InStep application writes to the step format, which is supported by almost all major CAD applications. So this covers the conversion of feature-based designs, and in general the feature-based conversion is aimed at things like PCBs and other mechanical designs that have a very clear geometric design. With that, we're going to take a look at a different type import. We're going to go to Import, Open, and we're going to change the file filter, and we're going to take a look at something that's a little bit more complicated and that can't easily be converted with a feature-based conversion. So this design is generally rotationally symmetric except for the threaded section, which does not follow a clear symmetry. If we take a look again at the features options and take a look at the preview, we'll find even though it can actually recognize a number of the cylindrical features, we are still left with several thousand triangles, specifically in the section where the thread was explicitly modeled into this. The application generally can't convert items like that very well just because it doesn't have a base geometry like cylinders and cones that it can rely on. So in this case, we would not want to take this approach. We'll click cancel to undo that. For this purpose, we're going to take the specific reverse engineering tools available. Here we have the two options, the surfacing and the slicing. We'll cover the surfacing in just a minute, but for now we'll take a look at the slicing option. We're going to go to slicing, and we're going to first create a new slice. This brings up the create slice dialog box where we can pick coordinate planes from surface or other options. These will depend on what it is you're trying to intersect, and you may have to play around with these a little bit to get a better feel for your case. Here, because we can see how the body is parallel to the z-axis, we're going to use an XZ plane as a way to intersect this. We can also go ahead and pick a point, and it will give us a preview of this. Now we know that this body is actually located at the origin, so we could easily just go ahead and set this to 0, and that way the plane goes to the origin. We can also go ahead and use the more advanced point creation tool. And in this case, again, we have multiple options available that you can find more information about in the online help file. But here we're going to use the Arc Center, which is a very useful feature. We're going to turn off the point filter because we're not interested in points, we're only interested in edges, and we're also going to leave the snap turned on so that it tries to snap to a current edge. Going to select items, and it'll show us a preview of the available edges as we hover over them. If we pick an edge on the arc, it will automatically try and determine if there's a circle or at least an arc through that edge. In this case it can find one, and it gives us the information about that. It also shows us a point where the center will be located. So this looks fine. We click OK, and if we're happy with where the plane is located, click OK to create that slice. Now we can see the intersection of that line with the body. If we're happy with that data, we can either export it to a step file, in which case it will create a set of polygons that go through the intersection, or more likely we can do an export to a DXF file. For the DXF files, there are a few options available under the settings. A few to point out are that we can turn on or off whether or not we want it to try to find arcs, and whether or not we want it to combine continuous lines into one. And we have several tolerance options that we can apply for that as well. It should also be pointed out that we can have each layer or each individual section exported to a separate file if you can find those, or if you should try and keep them all in the same file. We're going to turn this off so it writes all to one file. The minimum content really defines whether or not the output DXF file contains header information and so on, or if it's just meant to contain only the geometry. Generally going to want to turn this off or leave it off, as most applications expect some amount of content. The rotate DXF defines whether or not the output data is first projected onto the XY plane, or if it's meant to stay in whatever orientation it's found in. Most applications will only accept data that's located on the XY plane. So with these slices, we're going to go ahead and we're going to export those to DXF, and we're just going to call this slice. I'm going to import these again into a Libre, as this application can use those as sketches. The file units will depend on your scenario. You may want to change this to millimeters or whatever if you're using a Libre. So after just a few seconds, it imports the lines and any arcs that it found into its sketch preview, or its drawing management tool in this case. Well, what we want to do here most likely is activate the sketching tool, then select the lines that we're interested in, copy those with Ctrl+C, and then create a new sketch from those lines. So here we would then go in, pick a plane, copy V to paste, and now we can see the actual lines that were copied across. So in this case, because we know it's centered on the y-axis, we don't really need the other side, so we can delete that. We may need to check the sketch for issues. So once the sketches are acceptable, we can deactivate, and we would then just go ahead and create a revolution of this sketch around the y-axis. And here's the output of this process, and you can see it's very quick. It's very easy to work with these sketches for items that have some amount of symmetry or some kind of projection that we want to work with. So again, we're going to leave this here, close out, and now let's take a look at a different form of reverse engineering, specifically one that's related to more organic shapes. In this case, we're looking at a 3D scan of a sculpture that is available online. You can see our website for references to the creator of this. And we can also see that it's got a relatively large number of features. If we were to just follow the normal process of exporting this to STEP, which we're going to do here for reference. So in this case, this process actually takes several minutes, and we see that we end up with a file that's approximately 100 megabytes in size. So you get about 1 megabyte per 1,000 features. Now, obviously, a number of CAD applications would have a hard time importing this, and we're not going to go down the process of doing so, but know that it is actually possible to import files directly. If we take a closer look at the edge information though, we can see there's a lot of triangles, and one option you might consider is to simplify this and get it down to a level where you can directly import that. However, because this video is about reverse engineering, we're going to take a look at a far more efficient way of doing this. We can go to the reverse engineering tab, and this is where we're going to use the surfacing tool. Now, the surfacing tool is very powerful, and it contains a few options that we want to keep in mind. There's 3 sections to the surfacing tool. We got the seed mesh, we got edit mesh, and we got the generate option. Under the seed mesh, we have the auto generate seed mesh option, the import seed mesh option. This requires an OBJ file, and we have a manual option to generate a seed mesh. We can also delete the seed mesh if we don't want it, and we got again a few settings that we may want to take a closer look at. Under the settings, we have several options for the manual. So we got the number of segments, which we'll cover in a second, and we got some automatic tools as far as ordering and snapping. We also got automatic mesh smoothing, which are generally set to values that you want to keep. For more information on how these affect the model, please take a look at the online help files. The resampling is important in that it allows us to define the level of sampling that we apply when we initially generate a seed mesh, and we'll take a look at that in just a second. The recommended option here is to use the automatic seed mesh generator. If we click on this, we get asked to define the number of patches and whether or not we want to use that resampling that we just spoke about. Resampling just takes the entire body and breaks it down into a number of cubes. The number of cubes is directly defined by those values. If we set the value a lot higher, then it will sample at a very high frequency. Generally, you want to keep that at its defaults, but it's worthwhile experimenting with that if you get unexpected results or if you're looking for something very specific. The curve sample points is just a number that defines how many points are sampled between corners, and we'll take a look at how that affects the outcome in a minute. The patch count is the most important parameter here. It defines how many individual NURB surfaces this body is to be broken down into. It will try and reach this number or just below it depending on internal quality metrics. Generally, this can be set at any value between the maximum facet count, and you'll see this is either 100,000 or 1/2 of the original, whichever is smaller. And at the lower end, we can go to 1% of that. It should also be noted that you can manually override that, but the lowest value you can set is 100. So anything below that will not be acceptable. In this case, we're just going to set this to 1,000. We're going to leave resample on, and we're going to leave sample points at 4. When we hit generate, and this is just for the preview, the application will then convert that into a seed mesh for preview. It's always recommended that you take a close look at this output as it can contain some issues. In general, however, the result should be relatively good. We can also see there's some areas where the output is not a nice shape. So what we can do is we go into settings and then increase the smoothing factor to say 0.5 and the number of smoothing iterations to 5. If we click generate again, you'll see that the mesh updates just slightly in some areas. In this case, we're actually left with a mesh that looks relatively good. Now we can also say that we have regions where we're very interested in keeping a lot of detail. So for example, the nose might be one, the lips might be another, eyes, etc. In that case, we can go under Edit Mesh, and we can look for the subdivide option. And this is a toggle on, toggle off type button, so we can turn it on by clicking, and then as we hover over the mesh, it'll highlight the underlying patch. If we click on an area, it will create 5 patches from that one patch. So if we click here, you'll see that it's now subdivided that into several smaller patches. And we can extend that to several regions. When we're happy, we can turn that tool off again. So in this case, we're just going to leave it at that, and we're going to go ahead and click Generate. Now note that Generate is the point where it converts the original data down into NURBS patches. After just a few seconds, it will update the display and it will replace the original data. You also get on the side feedback about what the actual number was that it found. In this case, we ended up with 980 NURBS surfaces. If we turn on the edge display, we'll only see those patches. And again, like we saw, there's more detail around the lips and mouth area. So at this point, we could go back to export and write this to a file, but there's actually a shortcut here, which is just the surface option. This does exactly the same thing as the export, with the only difference that if we had multiple bodies or we didn't delete the original body, it would only write the actual NURBS body to file. So again, pick this file, click Save and overwrite it. Note that in this case the output is reduced down to 7.7 megabytes, and this only took about 8 seconds to complete. If we don't like the output, we can go back in and just from File, reload the previous file. Then under Reverse Engineering, let's take a look at the number of surfaces that we can reduce this down to. If we set this to say 200 and click Generate, then we see that the entire body has been represented by only 200 patches. Now, you might be interested to know that the number of sample points is the number of points that the application will insert between each of these corners. So in this case, we have the corner points and then 4 additional points in between that it will sample at. Note that this should only be increased to about a maximum of 10. After that, the application will start having issues with the number of samples that it needs to find. It should also be pointed out that this number will directly affect the style of surface that we can export. So if you keep this at 4, we have the option of using linear, quadratic, cubic or quintic style surfaces. If we reduce this down to 3, then we no longer have the quintic option. So we're going to leave this at its defaults, and we're going to go ahead again, convert this body, and now we see we're left with 193 NURBS surfaces. In this case, a lot of the features have been removed just because they can't fit into that definition. But generally we still have the same shape, and if this was only for a representation of some kind, then this would be sufficient. One other option here is to, rather than using an automatic surface, we can go in and manually define a surface. This might be interesting for cases where we're only interested in certain sections. Clicking this option brings up the manual NURBS seed tool. In this case, we first select point 1, and as we hover over the shape, we can see that we have a blue pointer. We click point 1 and it automatically goes to point 2, 3, and 4. Once it's done, click Apply and it'll give us a seed surface. Note that you'll always want to have these snap together. So for the second section, we want to make sure that we get close enough to the original point and then work from there. One more option that we have is that we can actually go ahead and generate an automatic mesh, and we're going to use a size of 1000 for this case. We can click Generate, and once the mesh is complete, we can export that seed mesh to an OBJ file. Now what we can do, and I'm going to use an older version of Blender for this, we can import that file, and then we can manually modify this. So for example, if you wanted to change some aspects of these facets, we can directly do so in whatever polygon editing tool that you're familiar with. So in this case, we may want to modify some of these facets around the eyes. Just so that we have a better shape mesh. It should also be pointed out that if we use a polygon editor that only works with triangles, as long as the triangles are continuous, the application can work with them. So once we're happy with this, we just go ahead and export this back to an OBJ file. And now what we can do is we can import this as a seed mesh to use. And you'll see that this section around the eyes will be modified. It should be noted that the imported file will be projected onto the original surfaces. So if they've moved a little bit, that is most likely due to that. We can also use that in various ways to generate a seed mesh over the target body that matches different parameters. If we're happy with this, again, we do the conversion to NURBS, and then we can go ahead and export that. We can use Alibre again to import this file. Now, after just a few minutes, the import will complete. However, it should be pointed out that there's often the chance that some errors will be encountered. If we take a closer look at that, that is often related to things such as overlapping surfaces or similar. So it may be necessary to go back in and make corrections, or make those corrections directly in your CAD application. Perhaps one thing to look at is if we set these values to high resolution. So it is certainly possible to set these values to very high resolution. On the surfacing, we can always set this patch count higher. So for example, if you went with 20,000 patches, and keep in mind that the number of sample points should be relatively low. So you don't want to go much above 5 or 6. About 10 is the highest the application can usually handle. If we leave this at 20, hit generate, we'll see the resultant mesh, and it should be pointed out that obviously the higher this number goes, the longer it'll take and the more memory it will consume. But we often end up then with a mesh that is far more aligned with the coordinate axis, as you can see here. All these facets are a lot straighter and more aligned. So keep that in mind as you go higher in the number. It should also be pointed out that you can go to the bodies option and do a remesh or a simplify or a smooth prior to running these tools. Exactly what kind of workflow you pick will often depend on the type of file you're working with and what kind of end results you're looking for. So let's go ahead and set this value to something like 5,000. At this level of resolution, we get a lot of detail, and we can also see that there's not a lot of edges that seem to intersect in any bad way. So this will be acceptable. So we can click generate, and we can see that the result is actually a very smooth body with a lot of details in the face and other areas. If we turn on the edge display, we can get a closer look at that. Again, keep in mind that you always want to start with a process whereby you use a coarse value and then you gradually work your way up from there. For additional information about this tool and others like it, please also take a look at the online help pages. This completes this deep dive video.